On January 3rd, 1961, the first fatal nuclear reactor accident in the United States, an uncontrolled nuclear excursion, occurred at the Atomic Energy Commission's SL-1 facility at the National Reactor Testing Station, better known as NRTS, in Idaho. All three men performing maintenance on the reactor during shutdown were killed. Immediately after the accident, a three-phase recovery program was initiated. Phase 1, lasting 6 days, consisted of executing pre-planned emergency procedures, recovering the casualties, and determining the extent of radioactivity release to the environs. During Phase 2, from January 10th, 1961 to late April 1961, Combustion Engineering Incorporated, the SL-1 operating contractor, was responsible for determining the nuclear safety status of the reactor. Safety being a paramount consideration, no personnel were allowed to enter the reactor building during this period. All investigating, viewing, and probing was accomplished with the use of remotely operated equipment. With the aid of TV systems, photographic equipment, and water and temperature detecting probes, the core was determined to be devoid of any moderating water, and the reactor was declared nuclearly safe. The Commission has issued a separate motion picture on phases 1 and 2 of the SL-1 accident. Phase 3 of the accident recovery effort was aimed at discovering what caused the nuclear excursion. A contract for this portion of the operations was awarded to the General Electric Company. Its responsibilities were to gather evidence pertaining to the accident, prepare the facility for core removal, recover the core for examination, demolish the reactor building, decontaminate the SL-1 site to habitable status, and as a fact-finding group, present an accident analysis to the AEC. To understand Phase 3 work better, it is essential to review the situation as it existed before and after the accident. The accident occurred in the reactor building, which is divided into 3 main areas. The uppermost section contained an air-cooled condenser with associated louvers, fan, and motor. The middle portion was the main operating area, where the reactor head was located, slightly below floor level. The control rod drive mechanisms penetrated the reactor head. Biological shield blocks surrounded the head during operation. The lower portion of the building housed the reactor vessel with a core in the lower region. Around the core was a gravel biological shield. During the interval between January 3rd and May 17, 1961, the state of the reactor operations room had not been disturbed. Essentially, all items and debris were in their original post-accident location. The shield blocks were in the same place as in pre-accident maintenance, having been moved back for access to the reactor. Vessel insulation material, steel punchings, fine gravel, and blotting paper were strewn over the floor. One of the control rod shield plugs, ejected from the vessel head nozzles, was lodged in the damaged ceiling. 2 other shield plugs could not be accounted for, but were later found in the overhead fan room. A 4th plug was observed to be lying across the reactor head. Any attempt during Phase 2 to move or disturb this component might have jeopardized nuclear safety. For example, by causing precariously perched fuel to fall into the core region. Remote viewing access to the vessel interior was limited to the only nozzle that was completely unobstructed. However, evidence that the core was dry permitted removal of the interfering plug by remote means. TV monitoring greatly facilitated this task. Greater photographic exploration of core damage was now possible. The plug was taken to one of the laboratories used for analysis work. This work proceeded simultaneously with a site recovery effort. Now, before commencing extensive decontamination efforts on the building, definite steps were taken to prevent physical hazard to working personnel. As standard procedure, participating personnel were thoroughly briefed beforehand at a control point 500 feet from the SL1 site. Each man was made aware of his assignment, the time allowed, health physics procedures, and what to do in case of unforeseen accidents. Nuclear detectors installed soon after the accident were routinely checked to ensure their operability as an early warning in the event of further nuclear activity. The reactor was deemed nuclearly safe as long as nothing was done to change its unmoderated status. Threatening this status was a 1,000-gallon tank of demineralized water suspended from the ceiling of the reactor operations room. On June 2nd, 1961, the first personnel entry into the reactor building since January 9 was to drain the tank in the operations room. The crew attached a garden hose to the tank and drained the water to the ground after making sure it was free of contamination. Another early safety precaution was the removal of oxygen and acetylene bottles and other readily combustible materials from the operations room floor. In event of fire, water could not be used for fear of causing another criticality should it get into the core. Evaluation of various plans for core removal and site cleanup depended on knowing the pattern of radioactive contamination within the building. Synchronized photo and radiation surveys of the operations floor indicated a nearly symmetrical zone of radiation. In the 5 months since January 3rd, the levels had dropped from more than 1,000 R per hour to approximately 150 R per hour over the reactor, decreasing radially to approximately 30 R per hour at the building perimeter. To determine how much of the radiation was coming from the reactor proper, the bags of lead shot were inserted into the open reactor nozzles. This lowered the overall radiation less than 10%, confirming that the accident had spread high-level contamination throughout the building. Also, that a major decontamination program faced the contractor. Scattered insulation and blotting paper had tended to concentrate the contaminated water from the reactor vessel into high sources of radiation. Recommendations based on the contamination study were made to an ad hoc committee which had been appointed by the AEC to evaluate and propose final disposition of the SL1 reactor. A plan was agreed upon for removing the reactor vessel, complete with core, to a large hot shop at the north end of the site for dismantling rather than dismantling them in place. By June 1961, lower radiation levels and the assured nuclear safety made it feasible to proceed with direct rather than remote decontamination and dismantling of the building. December 1 was set as the target date for removal of the reactor vessel in order to avoid adverse winter conditions. Donning anti-contamination clothing, large numbers of recruits assisted in the cleanup activity. Each man wore a belt containing 18 film badges to monitor the highly directional beta radiation exposure. Complete taping and masking controlled body contamination and inhalation of radioactive aerosols. Fine particulate material tended to penetrate even 2 sets of coveralls, so a disposable plastic suit was worn for additional protection. Self-reading dosimeters were taped to the suits to provide on-the-spot monitoring of exposures from radiation. Vacuum cleaning was a major decontamination technique. An improvised vacuum system developed through operating experience consisted of 50 feet of hose running down from the working area to a 15-horsepower positive displacement rotary blower with a shielded 55-gallon collection drum and bags mounted on a truck bed. Gross clutter such as iron punchings, blotting paper, and insulation had to be shoveled into cans. These cans now represented new concentrated sources of radiation and were removed by remote means through the freight door. Another remote removal method was the use of an electromagnet to remove iron punchings from the higher fields of radiation. It met with limited success. All loose debris retrieved from the floor was shipped to the hot shop for inventory. Every item that might improve understanding of the accident had to be examined. As the cleanup progressed, the contaminated concrete blocks proved to be major obstacles as well as being sources of radiation. The heavy blocks were skidded across a greased steel apron to the freight doors and allowed to drop onto a pile of sand, which served as a shock pad to prevent breakup. To minimize exposures, cleanup near the reactor was left until last. This area, including the reactor head, was now the highest source of radiation. Temporary shielding in the form of a 2-inch steel plate was placed over one particularly high source of radiation next to the reactor. Also, bags of lead or steel shot were placed over and around the head. Radiation on the operations room floor, except over the reactor head, was now down to 15 R per hour generally. But a radiation survey of the ceiling indicated major levels of radiation. The excursion had forced contaminated water and debris through holes in the damaged ceiling. Originally, a ladder and narrow airlock provided access to the fan floor. Safer and easier access was gained by cutting through the outside wall of the building and erecting a large outside stairway to the fan room level. Preceded by a health physics survey, a photographer entered the reactor building to obtain photos of the general conditions. These photographs were used to brief personnel, spotlighting key items to be collected as cleaning progressed, such as shield plugs, pieces of drive racks, and broken C-clamp. Floor vacuuming was again employed, followed by placement of 1/4-inch iron plate on the floor for personnel shielding. Cleaning efforts continued alternately in the fan room and immediately around the reactor head as radiation levels dictated. During the first 2 months of Phase 3, entry times were in the order of 1 to 3 minutes, resulting in a total of only 16 man-hours of cleanup in the reactor building proper. A bell alarm system installed in the working areas was used to control how long workers could stay in the reactor building. Despite general cleanup of the fan loft, radiation sources in excess of 50 roentgens per hour remained within the relatively inaccessible parts of the condenser gear. In order to lift the pressure vessel, the fan, condensers, and ducting had to be removed. The contaminated fan room components were cut from their mountings and lifted from the building. Safety ropes were required for all high elevation work. To protect the reactor vessel from inadvertent flooding by rainwater, a protective plate was placed over the roof hole during non-working hours and bad weather conditions. The removed equipment lying around in the SL1 yard soon posed an additional problem in the form of unnecessary background exposure to personnel. A careful study confirmed the desirability of opening a new burial ground specifically for SL1 debris. The survey indicated that 81,000 cubic feet of burial space would be needed. The estimated personnel exposure that would have been required to cut, package, and transfer the contaminated equipment to the existing NRTS burial ground would have exceeded the contractor's allowable exposure for a 3-month period. This consideration alone justified opening a new burial site 1,600 feet away from the SL1. Also avoided was possible contamination of 13 miles of site and public roads leading to the more distant NRTS burial ground. All material not being directly examined for accident evidence was transported without any decontamination to the burial trenches north of the SL-1 site. The trenches were backfilled to approximately 2 feet of overburden, or until radiation readings were less than 1 MR per hour at the ground surface. Removal of the grossly contaminated equipment enabled personnel working in more tolerable radiation fields of less than 5 R per hour to prepare the vessel and building for extraction of the reactor. The core structure had to be carefully inspected to verify whether it could withstand the 40-mile transport to the hot shop. A borescope examination of the underside of the core through an 18-foot-long hole bored through the gravel basin vessel wall indicated that the core structure would remain intact during the move. Some 60 photographs were made through a 26-foot borescope which contained its own light source. Large segments of insulation from around the vessel walls were found on the reactor room floor, indicating that the vessel may have raised several feet at the time of the excursion. A trial lift of the vessel was performed with a building service crane. This operation confirmed that the 13-ton vessel had jumped, shearing off the steam outlet and feed water pipes. This freed it to be raised from its supporting shell. Observers actually saw the sheared steam outlet as the vessel reached the peak of its 3.5-foot trial lift. The entire operation was monitored and directed with the aid of closed-circuit TV. The vessel was now ready for removal as soon as a 7-foot hole could be cut in the operations room ceiling to accommodate the actual lift. Partial cutting away of the fan room walls also was necessary in order to allow clearance for the bottom of the vessel and optimum positioning of the 60-ton capacity crane. To minimize the possibility of mishap, a complete mock-up operation was conducted just prior to the actual transfer. A concrete cylinder of approximate dimensions and weighted with gravel was used to test clearance, positioning, and maneuverability for the final lift. The simulated vessel was test hauled to the site in an available concrete cask, which was to provide radiation protection during the transport of the vessel and core. Additional gravel was spread next to the building to afford a level pad and a contamination-free surface for the truck tires. The mock-up exercise showed that 6 inches of additional building shell had to be removed to attain the necessary clearance. To contain and minimize the spread of contamination from the vessel proper, rubberized canvas with elastic bands was positioned over the top of the reactor on a steel frame. As the vessel was withdrawn, the accordion-like shroud automatically enveloped the vessel. As a final precaution against contamination, the tractor and lowboy trailer were covered with sheets of plastic. The actual lifting and removal then proceeded smoothly. The entire operation, including transfer of the vessel to the trailer, required about 20 minutes. Radiation levels around the unshielded vessel during the transfer measured about 9 R per hour at 25 feet. Prevailing good weather contributed to ideal operating conditions. The metal top was used to confine any loose contamination during transport. The following morning, November 30, 1961, the truck and cask were stripped of their protective plastic covers and steam cleaned. Direct radiation readings were only 40 to 50 milliroentgens per hour at the surface of the cask. The 40-mile trip to the hot shop was accomplished without difficulty in less than 4 hours. The route had been cleared of overhead obstructions to accommodate the 24-foot high load. Precautionary surveys made sure that all bridge capacities were adequate for the 52-ton weight. The caravan, complete with emergency crews and tire changing equipment, did not disrupt the normal flow of traffic. The 6-story, 160-foot-long hot shop, equipped with remote manipulators, was ideally suited for the extensive task of vessel and core examination. It was originally used in the aircraft nuclear propulsion program. After removal of the vessel, there remained the work of raising the silo-like reactor building and decontaminating the adjoining buildings and grounds. The fan room walls were cut with torches and removed with a crane. The heavy fan room floor was cut into 3 segments. The largest section with supporting I-beams was removed last. Despite the unique problems encountered, only one minor accident occurred during the recovery work. Further reduction of radiation exposure was accomplished by cleanup of loose contaminated debris after the vessel removal. Then followed removal of the operations room motor control panel, purification panel, turbine generator, pumps, piping, and walls, and eventually the stairway. Practically all that remained at that point was the concrete reactor operations floor and the lower shell of the building filled with gravel, which was spilled through weep holes and removed for burial. The 700 cubic yards of gravel was not highly contaminated as originally estimated. It ranged from 3 MR per hour for a handful of gravel taken from near the outside wall to 10 MR per hour for a sample that adjoined the reactor vessel support cylinder. Particulate airborne contamination was held to a minimum, and careful surveillance was maintained by health physics personnel. It was decided that blasting would simplify removal of the 70-ton concrete floor. Preparation for this included cutting the wall, removing the superstructure, and placement of fallout paper at strategic locations to monitor aerosol contamination resulting from the blast. 2 experts were called upon from the Army Demolition Section at Fort Belvoir, Virginia, to cut the 6 remaining I-beams supporting the concrete slab. 2 days were expended in planning the demolition job, including preparation of the composition C explosive in shaped charged trays. The explosive was strategically placed to make sure the slab of concrete and steel would not fall against the surrounding buildings. The blast attempt was successful with the aid of a bulldozer pulling on a cable. The slab was sectioned and dragged to the burial ground. Trucks then removed the remaining gravel and the steel support cylinder. Sectioning and disposal of the base plate upon which the entire building was erected came next. The remaining steel reinforced concrete piers, which supported the entire structure, yielded only with the help of a bulldozer and cutting torch. The radiation level at the surface of the ground where the reactor stood was finally reduced to less than 1 MR per hour by blading and backfilling with clean gravel and dirt. In all, it took 5 months to complete demolition of the reactor building. Meantime, decontamination of the adjoining buildings went forward using proven techniques. Vacuuming was ideal for decontaminating porous acoustical ceiling tile. The loose insulation in the attic of the support building was contaminated above allowable limits. It had to be removed by hand or by vacuuming. Salvageable items, such as telephones, desks, chairs, vending machines, tools, machinery, and control room equipment, went to the control point for decontamination. The more unwieldy or complex items were transported to the decontamination area. Gross steam cleaning and acid baths were employed on heavier equipment. The more delicate instruments were hand cleaned. High-pressure hosing of the exterior metal walls aided in reducing the levels of loose contamination. Smear samplings monitored the effectiveness of decontamination at every step. Surveys made after each general cleaning determined the next course of action. The site grounds were scraped twice. Loose contaminated dirt was hauled to the burial ground. No heavy-duty equipment and vehicles were permitted to leave the contaminated zones before being steam cleaned. Next, a meticulous health physics survey revealed the remaining difficult and localized hotspots. These were removed with a shovel. Temporary roads, constructed to facilitate the recovery operations, were rolled up toward the burial ground, thus leaving a clean area behind and concentrating the remaining contamination in an ever-decreasing area until the last radioactive debris was contained. Personnel leaving the restricted contaminated zones shed their anti-contamination clothing in a trailer adjacent to the control point. They underwent complete monitoring inside a steel cubicle. Its purpose was to minimize residual background radiation from the surrounding area. No significant body contamination occurred during the recovery. Health physicists carefully recorded the name, time, and exposure for each personnel entry. Only 3% of the exposures exceeded the established limits of 3 rems per quarter whole body or 10 rems per quarter skin dose. The highest whole body exposure was 3.21 rems. Whole body counting sampled the effectiveness of face masks in preventing the inhalation of contaminated aerosols. In no case was there observed any whole body burdens above 10% of the recommended guide values. The badge belt was devised for obtaining a representative dose for the highly erratic and short-range beta radiation. It was recognized early in phase 3 that the skin dose, beta plus gamma, would be the limiting criterion for personnel exposures. Thus, the beta exposure was computed from the average beta to gamma ratio determined from the 18 badges around the waist. In general, the ratio varied from 4.5 during the cleanup entries down to 1.0 during the final stages of gravel removal. Whole body exposures during phase 3 were accumulated rapidly during the initial cleanup activity. As the project drew to an end, the exposure rate diminished to result in an overall expenditure of 1,140 rems whole body. The average exposure per active participant was 2.6 rems for the entire 13 months of phase 3. The same is generally true of the accumulated skin dose profile. The total of all exposures for all personnel during phase 3 was 3,850 rems skin dose. The recovery program, beginning January 3rd, 1961, lasted 18 months. The whole body exposure data showed a high rate of biweekly expenditure during the phase 1 emergency period. This was followed by a relatively low rate during the 4 months of phase 2, when no entries were allowed into the reactor building. This rate then increased for the phase 3 effort, during which the building was being dismantled and decontaminated. Gradual reduction in the rate followed as decontamination efforts took effect. A total of 1,240 persons participated in the recovery effort, of whom 790 were working in radiation fields at the SL-1 site. Most of them were affiliated with Combustion Engineering, H.K. Ferguson Company, General Electric Company, AEC, and the U.S. Army. Early in Phase 3, hot cell and laboratory analysis of evidence reclaimed from the reactor building was providing important information. Control rod racks, nuts, seal housings, washers, C-clamps, and many other items were retrieved and decontaminated. These were then examined and sectioned or reassembled to understand better the part they played during the accident. A review of the SL-1 control rod drive mechanism will make for better understanding of the hot cell and laboratory analysis work. The components are scram shock spring and housing, shield plug body, guide tube, rack, extension rod, connecting rod, and the control rod blades which regulated the power output of the reactor core. Particular interest focused on the central control rod drive assembly. It was carefully dissected and examined for telltale evidence. As found, the central control rod appeared only slightly withdrawn. However, upon matching impact marks and scratches on the inside of the rod guide tube with those on the extension rod, it was revealed that the central control rod might have been almost entirely withdrawn at the time of the reactor excursion. Shield plugs for the outer control rods also underwent close scrutiny. This showed that an exceptionally high pressure had developed at the underside of the vessel head during the excursion. The magnitude of the high pressure was reflected in pronounced pinching and distortion of the extension tubes. Also in collision damage to the spring housings and flanges. But the reactor itself continued to be the main focus of attention. Examination of the vessel internals could now proceed by direct means. This would not have been possible but for the partial shielding afforded by the cask. Technicians were able to look through the existing steam outlet hole with a borescope into the vessel interior. The borescoping revealed that all internal head connections were severed and head removal could proceed. Bulging of the vessel wall had caused the stud bolts on the flange to exert an inward pinching force on the head, making its removal difficult. The task was accomplished by driving wedges between the head and vessel flange with a crude, though effective, pendulum hammer. An unobstructed direct view of the vessel interior was now possible with the aid of a mirror and direct photography. The central control rod blade, locked in its shroud, could be seen lying on top of the damaged core. Removal of the central blade and shroud laid bare the true extent of damage to the reactor. The core was radially expanded and wedged against the thermal shield. Feed water spray rings were collapsed. The 16-element central region experienced severe melting, mechanical distortion, and complete disarrangement. A number of flux wires inserted just prior to the accident were also visible. The 24-element outer sections were squeezed between the disfigured cruciform shrouds and the thermal shield. Traces of solidified boric oxide could be seen as white streaks on the inside wall of the reactor vessel. Later, more detailed examination revealed a post-incident water level mark on the shrouds at approximately the same height as the top of the fuel elements. Core examination was augmented by boring 8 2-inch holes around the perimeter of the vessel below the bottom of the core and thermal shield. Through these holes, photographers obtained pictures of the entire bottom structure of the core and debris lying on the bottom of the vessel. The bulged vessel was then lifted from the cask and inserted into a holding fixture. Next, an 8-inch hole was bored through the bottom of the vessel. The drill bit cut through the 3/4-inch steel like a big cookie cutter. This allowed a large section of debris from the bottom of the vessel to be removed and examined. It was intended to recover the debris undisturbed to study material thought to be in sedimentary layers. However, during the sample removal operation, the plug was upset, thereby destroying any evidence that might have been gained from possible sedimentation. While the remaining debris was being scraped out, a TV camera with a monitoring screen in the gallery was positioned outside one of the 2-inch holes in order to observe and direct the cleaning operation. Next, a critical experiment was conducted as an aid in determining the shutdown mechanism and to assess the possibility that multiple excursions had occurred. A specially adapted framework was placed in the hot shop to accommodate the experiment. The vessel was suspended by its flange into an aluminum tank deep enough to envelop the core area. Water could then be introduced into the vessel under controlled conditions through the 8-inch hole in the vessel bottom. It was conjectured that the addition of water to the water level ring found at the top of the core might add enough moderating medium to achieve criticality. 5 times the vessel was filled to 6 inches above the core without achieving criticality. 3 of the filling operations used diluted acetic acid for washing boric acid from the fuel region. The last of these fillings was heated to 160 degrees Fahrenheit to speed the dissolving process. Samples of the dump water were obtained to analyze the effectiveness of boron removal. All but a trace of boric acid was washed from the fuel plates. The final filling was performed with demineralized water, and, as in previous fillings, very little neutron multiplication was observed. It was evident that the core was left greatly subcritical as a result of the accident. The effective multiplication factor was about 6/10, which is considerably below unity, the amount necessary for a self-sustaining chain reaction. The experiment was then terminated and preparations for disassembly commenced. Dissection of the vessel and core started with horizontal cutting of the vessel just below the top of the thermal shield. Removal of the top half of the vessel exposed the upper parts of the control rod shrouds. Manipulator access to the core was now greatly improved. The loose fuel plates, fuel elements, the core support structure, and shrouds came out with little difficulty. The radial force of the excursion was apparent in the concave appearance of the outer control rod shrouds. All core parts were set aside in trays for analysis in the radioactive materials laboratory. Lastly, the thermal shield was extracted and the pressure vessel bottom completely vacuum cleaned. Central rod and shroud examination obviously took preference over other core components. The blade was observed to be bound in its shroud at a withdrawal distance of 20 inches. That the central blade did not slip within its shroud after the excursion was proven by the matching impact prints of the shroud circulation holes on the blade surface. Also by fuel residue splattered on the shroud and through the holes onto corresponding areas of the blades. Matching longitudinal rub marks found on the shroud and blade cladding were interrupted by oxide flaking or impact marks from the shroud weep holes, thus indicating these rub marks were of pre-incident origin. The blade was cut in sections to provide chemical and metallurgical specimens for examination by SL1 recovery personnel and requesting organizations. Gross accountability of fuel and burnable boron strips was undertaken by examining each element and plate, recording its identification number, approximating the amount of fuel or boron remaining, and mapping the results. From this, it was deduced that the severest core damage was around the central control blade, decreasing radially outward. Approximately 50% of the center 16 elements had completely melted or otherwise failed. Flux wires running through the middle of these melted elements were relatively undamaged, however. Despite the high rate of fuel melting, cladding rupture, and the spewing of melted fuel, the immediate transfer of heat to the water left the adjacent aluminum cobalt flux wires unmelted. The remaining boron strips were gray in color, obviously brittle, and easily broken by hand manipulators. Approximately 92% of the fuel originally within the core was recovered from inside the reactor vessel. The remainder escaped from the vessel at the time of the accident. Fission product release was about 5%, which is not in complete agreement with the observed loss of fuel. Debris from the bottom of the vessel was sifted according to mesh size. Laboratory analysis revealed the major constituents to be uranium, aluminum, boron, iron, and indissoluble oxides. Gross examination of the outer control rod blades revealed no movement from their relative rest positions in the core during the time of the accident. The undercore support structure was badly bent and twisted. Experts were called upon to examine the core for telltale signs of a chemical explosion. They found none. Representative boron strips, fuel plates, control rods, core structure, vessel walls, and thermal shield were sectioned for radiochemical, metallurgical, and physical examination and testing. The recovered aluminum cobalt flux wires, having no radiation history prior to the accident, served as excellent monitors for determining neutron flux profile and energy expended during the accident. The flux wire was of aluminum stock with tiny slugs containing cobalt in the shank every 3 inches. Meticulous care was exercised to decontaminate the wires, weigh, and dissolve the slugs, and count the specimens on a 256-channel analyzer. Then, by appropriately applying mathematical conversions, the flux numbers were obtained. After decontamination of the vessel head, shield plugs, and the center section of the reactor room ceiling, all items were reassembled in their original orientation for further studies to verify trajectories of the plugs and damage to the ceiling. Previously gathered evidence indicated that on the night of the accident, the 3-man crew was in the process of connecting the control blades to the drive mechanism when the excursion occurred. Now, this is the routine procedure they were believed to be following. First, the shield plug is slipped down over the rack. The pinion gear housing and spring housing follow. The pinion gear is inserted in place. The lifting tool is then inserted into the spring housing and threaded onto the rack. The rack is then lifted a few inches out of the housing to place the C-clamp on the rack. The handling tool is lowered until the C-clamp rests on the spring housing, thus holding the assembly in place. The handling tool is removed, and the retaining washer and nut are placed on the rack. The handling tool is screwed back on the rack. The handling tool and attachments are lifted to remove the C-clamp. It was near this point in assembly that the excursion occurred. Physical evidence shows that the nut, washer, and handling tool were on the central control rod at the time of the accident. The evidence was consistent with the possibility of hand withdrawal of the 85-pound central control rod blade to the 20-inch position. To test empirically that this is possible, a control rod drive mechanism was assembled over a pool of water, and attempts were made to withdraw the rod with reasonable efforts and maximum efforts. Similar tests simulating stuck mechanism conditions were also conducted. All data were recorded on an oscilloscope. It was concluded from analyzing the data that an average man could withdraw the blade fast enough and far enough to reach the observed 20-inch final position before steam generation terminated the power excursion. The experiment further showed that a 20-inch withdrawal would not likely result from trying to free a frozen rod assembly. The animated scenes that follow depict the complex sequence of events that are believed to have occurred during the accident. It is important to remember that the whole sequence probably took place in less than 4 seconds. The direct cause of the accident clearly appears to have been manual withdrawal of the central control rod blade by one or more of the crew members considerably beyond the limits specified in maintenance procedure. However, there was insufficient evidence to establish the actual reason for such abnormal withdrawal. Now in slower motion. Regardless of the withdrawal mechanism, the central control blade was lifted approximately 20 inches. This was 3 to 4 inches above its critical position of 16 to 17 inches. Approximately a 2% supercritical condition resulted, corresponding to a period of about 4 milliseconds. This supercritical configuration caused the rapid production of neutrons by fission for a total energy release of approximately 130 megawatt seconds. A metal-water reaction probably contributed 20 MWS additional energy release. The fissions occurring within the fuel plates increased the temperature of these plates to a point near or above melting, depending upon location in the core. In the center regions of maximum neutron flux, the fuel within the plates experienced vaporization temperatures and burst the plate cladding. Thus, the spewing of hot vaporized fuel rapidly produced steam in the surrounding water. The steam was generated at a rate far faster than could be dissipated, and the resulting outward expansion of this high-pressure steam bubble of at least 500 psi damaged the core. The central blade was seized by the shrouds surrounding it, and the two became an integral unit. At this time of seizure, the central blade was withdrawn about 20 inches. The steam being generated pushed upon the water that was above the level of the core, forcing the slug of water upward from the core zone. It was stopped by the vessel head, with a resultant water hammer causing peak pressures of about 10,000 psi. While the water was moving upward, the core structure jumped, reaching a height of 7 inches above its supports when the water hammer hit the head. As the water was decelerated upon striking the vessel head, the forces generated collapsed the shield plug guide tubes. It also deformed the vessel wall and the vessel head nozzles. Additionally, the momentum of this water, as it struck the vessel head, transferred its energy to the reactor vessel, imparting a vertical motion to the shield plugs and to the vessel itself. Some biological shielding material was ejected from its container on the vessel head. The vessel jumped approximately 9 feet, sharing the connecting pipes and expelling some of the surrounding thermal insulation. Simultaneously with the vessel lift, the pressure within the vessel expelled the unbolted shield plugs. The ejected shield plugs came to rest in various locations. Number 4 in the fan duct, number 3 on the fan floor, number 1 and number 7 in the operating room ceiling. The central plug hit the ceiling and fell back on the vessel head as the vessel dropped back to its original position. Reconstruction of the movement of the central mechanism gives greater insight into the physical damage observed on the rod. Initially, the rod was withdrawn approximately 20 inches. As a result of the core jumping during excursion, the central rod was moved upward an additional 7 inches. The water hammer pressure then bound the rod and tube together at this relative position of 27 inches. The plug and rod were accelerated as a unit from the nozzle by the high pressure. Upon hitting the ceiling, the handling tool snapped the threaded end of the rack, impaling the tool into the ceiling. The impact also broke the rack inside the plug and simultaneously caused the plug to slip back up the rod to the fully inserted position. The plug flange then hit the overhead structure and the fractured rack continued into the fan room. The plug fell back onto the vessel head, snapping the connecting rod after it had been driven upward through the plug about 3 inches. The scratch mark evidence and matching marks on the tube and extension explain the seeming discrepancy of finding the central shield plug with the final rod withdrawal position only 3 inches above the normal 0 position. The accident unfortunately terminated more than 2 years of successful SL-1 operation, during which valuable nuclear technology was gained. At the same time, lessons learned from the accident itself must be fully exploited for the betterment of atomic industry as a whole. Recognizing that future nuclear incidents, if any, will differ in degree and complexity, the SL-1 experience has emphasized several considerations. Extensive and detailed emergency pre-planning is a necessity for any reactor site if personnel are to be protected from hazards such as large radiation exposures. It is important that all necessary emergency equipment be immediately available. Adequate manpower available on short notice is needed to execute a recovery program as large as that of the SL-1. This manpower should include chemists, physicists, engineers of all kinds, nuclear consultants, physicians and nurses, health physicists, photographers, technicians, and laborers. Judicious management of radiation exposure is a necessity for any recovery effort of this kind. Large quantities of contaminated debris and high beta radiation present in the SL-1 emergency made it necessary to devise certain additional control procedures for adequate personnel protection. Reactor safety reviews of AEC-owned and licensed reactors are now even more frequent and detailed than before the accident and pertain to every phase of operations and design. Nuclear and physical characteristics of the SL-1 excursion are strongly influencing the hazard analyses for future reactor systems. Assignments of responsibility for reactor safety are more clearly defined. And there is a new awareness of the potential nuclear hazards which may exist while a reactor is shut down and routine maintenance is being performed. The recovery program proved that dismantling in place is not always necessary to obtain undisturbed scientific evidence. A damaged vessel and core can be successfully removed and transported long distances for analysis under laboratory conditions. The overall recovery program, including phase 3 as well as phases 1 and 2, cost $2.5 million. Losses in capital equipment totaled another $1.5 million. There has been a valuable return on these expenditures in the form of newly acquired data on nuclear safety and accident procedures. it is tragic that 3 lives were lost. Nevertheless, the information developed and the lessons learned will help prevent similar accidents in the future, will help save lives, and aid in the safe development of our nuclear technology. The SL-1 reactor building has been dismantled and removed, but a scientific legacy remains for all who are charged with the safe operation of nuclear reactors.